Hi, my name is Ashwin Whitfield, and this is my video lab report for Physics 2211 Lab Experiment 4. First, our lab introduction and background info. Lab overview and purpose. Our experimental setup is as follows. I use the sample video and tracker software to extract position data of an oscillating and swinging spring mass system. The purpose of our lab is to compare experimental and model data of a swinging oscillating system in order to visualize the changes in types of energy in such a system. And a preview of our results. The change of energy of the system is zero, and the experimental and model data diverged somewhat, but followed similar trends. Physics principles. First pertinent principle is Newton's second law, which states that the net force on an object equals the change in momentum over the change in time. This principle is important for our velocity and position update formulas, which can be seen on the screen. Our second pertinent principle is the energy principle, which states that the change in energy of a system equals the work done by the surroundings plus the exchange of thermal energy between the system and its surroundings. The types of energy that we'll be dealing with are the translational kinetic energy, the gravitational potential energy, and the spring potential energy. And because all of the items that do work are within our designated system, the work done by the surroundings, W, is equal to 0. So, the work done by our surroundings is 0, Q equals 0, so the delta E of our system equals 0. System and surroundings. Our system is our Earth, spring, and mass, and our surroundings is nothing, as nothing else does significant work on our chosen system. Initial conditions and pertinent equations. Here is our free body diagram for our initial static equilibrium position, and our energy change equation breakdown, seen at the top here. We are keeping in mind with this breakdown that the delta E of the system is equal to 0. Tracker details. Our start time is 0 seconds, our initial position is seen on the screen, and our initial velocity is 0 as the mass started from rest, and the final track time is 6.648 seconds, as seen in the models here. Computational model initial conditions. The mass of the ball is 0.402 kilograms, as specified in the pre-lecture videos, and the ball position and velocity are seen on screen, as specified on the previous slide. Our delta T is 0.095 seconds, as this is the time increment between frames in our video. Our G is 9.8. Our spring constant is 6.83, and our L naught is 0.123. Both of those values, the spring constant and the L naught, were calculated using the equations on screen here. K equals M over T oscillation 2 pi all squared, and L naught equals the magnitude of the L vector minus mg over K. These equations were derived on screen here. Our computational model. Our spring vector information is below, and that was inputted into our model below that, and our energy equations, as specified earlier in the presentation, were input into our model here. Net force and update equations. We know that our F net equals 0 at our equilibrium position, and so we can deduce our F net here, inputting the equations for the respective force due to gravity and spring force, and adding that equal to 0, and then using that for our velocity and position update formulas. Our while loop. Because all of the equations and procedures used in this section have been discussed previously in the presentation, I'll omit narration for the sake of time. Please pause and take a look if you'd like. Results. Results of our computational model can be seen here. The left is the change in energy versus time, and the right are the positions versus time. We can see that the y position versus time diverges slightly, and we'll discuss that on our next slide. The change in energy versus time graph. The change in gravitational potential energy in red, and the change in change in spring potential energy in green are opposite in sign and identical in magnitude. As one increases, the other decreases. The change in our kinetic energy also oscillates, but has a lesser magnitude than the other energies. For our position versus time graph, the x-coordinate versus time graph is more accurate to the observed data than the y-coordinate versus time graph, meaning that the model is more accurate when predicting x values than y values. And possible sources of error that could lead us to get these results are not accounting for drag, initial force imparted by man upon release, and hand-tracked position data. Conclusions. What does it mean? Yes, my model does satisfy the energy principle because the opposite signs and identical magnitudes of the potential energies cancel each other out, and the kinetic energy has the same sign as the potential energy for a given period, meaning that the change in total energy is equal to 0. What does it mean, number 2? To find our different oscillation periods, we find the time it takes to make one complete oscillation, peak to peak or trough to trough, based on the graphs seen to the right. Our x value base period is 1.6334 seconds, and our y value base period is 1.5194 seconds. The difference is 0.114 seconds. The difference in the period of oscillation may be due to camera distortion or hand tracking. Using either time period would yield a different spring stiffness constant, impacting the spring force and the spring potential energy. Thank you for watching.